Good evening, everyone. So today, the topic for today will be uh, contraction of skeletal muscles. Okay, so first we'll have to talk about the structure of a muscle. So you'll have, let's see, this is an arm, okay, forearm, as you know, biceps. Okay, so we'll take this muscle which we call the biceps. So it's made up of muscle fibers. Okay, so I'll take the muscle fibers. I'll take one muscle fiber and then I'll zoom on it. I'll zoom on the muscle fiber. So this is a muscle fiber. I'll look at it, and you can see, there will be smaller fibers, and these fibers are called myofibrils. So these are the units of muscles. So these are the smallest, you could say, smallest strand or working units of muscles, and myofibrils are made up of thick and thin filaments, which we are going to talk about. So as you can see, this is a sarcomere. This is a sarcomere. This is known as Z line, and another Z line. As you can see, it has a crisscross, which is why we call it a Z line. So most of our discussion will be here at the sarcomere. So let's have a recap of what we did the other day. So initially there will be an action potential down the neuromuscular junction. This action potential will cause the release of acetyl-CoA into the synaptic cleft. The acetyl-CoA will bind with the nicotinic type 1 receptor. This will cause influx of sodium into the muscle, so into the sarcolemma more specifically, and then this influx in sodium, it will generate an end plate potential, and the summation of all of these end plate potential, it will cause an action potential which will spread. It will spread so basically it will spread along the sarcolemma and then into the T-tubule. And then what will this do? First, it will activate the dihydropyridine receptor. You can see here. So it will activate the dihydropyridine receptor, and then this dihydropyridine receptor will activate the ryanodine receptor in the sarcoplasmic reticulum, which will cause an efflux of calcium out into the muscle, basically into the cytoplasm maybe. So this was the last thing that we explained in our last class. So to resume with it, so why calcium? Why do we need calcium? So first let's analyze the sarcomere. So as you can see, I have made this diagram. So this will be the base of your knowledge. So learn this well. If you know this, you'll know everything. Everything will be easy. So this is the thin filament, also known as actin. Okay, and then this block will be myosin. It's lagging So this will be your myosin, and then these small things will be your myosin head, and then this will be your titin. It's called titin, another protein. Okay, so the main ones are actin and myosin. So let's zoom in on actin and let's focus on it. So actin basically they are those round, you can say, balls. So there are two of them, they coil like so, as you can see. And on those actin there will be a protein which is known as tropomyosin. So what does this tropomyosin do? It prevents the interaction between the myosin head and the actin, as you can see. So you'll have a myosin head here, and it cannot interact with the actin. So this myosin head cannot interact with this actin. So what do we have to do? We have to remove this tropomyosin. So how do we do that? As we have studied previously, so we have calcium here. We'll take the calcium. As you can see here, there's another protein called as troponin. So as I told you, the hardest part of this is memorizing all of these proteins. So we will have troponin. There's troponin C, troponin T, and troponin I. Our main ones are troponin C, and troponin T. So basically what calcium will do, calcium will come and bind to troponin C. And what will this do? This will cause 1 second. This will cause, so basically the calcium will bind to troponin C, and the troponin T, it binds with the tropomyosin, so T4T, C4C, and then it will go conformational change. So basically what will happen, this whole strand will just move laterally. When it moves laterally, it will expose these active sites of the actin. Okay, so when these are exposed, what can the myosin do? It can interact with the actin. So I hope it's clear so far. So let's recap. You'll have actin, you'll have myosin, more specifically the myosin heads. You'll have calcium, which will come, it will bind with troponin. Basically there's tropomyosin on the actin, which is preventing the myosin head to interact with the actin. So the calcium will bind to the troponin C, and then the troponin will undergo conformational change. It will move laterally and expose the active sites of the actin. So now what do we do? As you can see, there's ADP and pi. So ADP and pi, these are residues from the previous contraction. So adenosine diphosphate and pi. So what these two will do, first pi, so phosphate, so the phosphate will leave it will leave the initially they are bound to the myosin head. So the phosphate will leave the myosin head, and what will this do? It will cause the myosin head to move upward, to move 90 degrees upward and attach to the active side of the actin. So now we'll have only ADP, and what will the ADP do? It will leave the myosin head and provide energy for the power stroke. So this is a keyword. So basically what the power stroke does, so the power stroke, basically you'll have your myosin head here. It will be like this. So it will move horizontally, it will come here while it's still attached to it, and then what will this do? This will pull the Z line. So there will be, it will pull it. So initially it's here, it will pull it, it will be here. The same happens here. So initially what will be done? There will be shortening of the sarcomere, and this is basically how muscle contraction works, by the shortening of the sarcomere. So once we have done this, we have done our power stroke. So the myosin head is now attached to the actin. So how do we basically free it? So we'll have an ATP. An ATP will come, bind to it, okay, and then the ATP, it will be broken down into ADP and pi, and what will this do? This will release the myosin head from the actin, and then this so we'll have ADP and pi, and then this will happen all around again. So pi will leave, and then so initially ATP hydrolyzed to free the myosin head. So it's now down. So the pi will leave, and then it will go attached again. So the sarcomere length remains the same. So once it's shortened, it's maintained, and like initially it was attached here, and when it moved here, so this comes here, so it will shorten, and then the next thing you will do, so it has already bounded to this. The next thing it will do, it will bind to this and then cause it to go this way. The next thing, it will bind to this and then cause it to go this way. So basically this is how muscle contraction occurs. And then for muscle relaxation, so what started all of this? Calcium started all of this. So what will we do? We will remove calcium. So on these sarcoplasmic reticulum, there's a protein called the endoplasmic reticulum, Ca2 plus ATPase. So what will it do? It will actively pump calcium back into the sarcoplasmic reticulum by using ATP. So it's an active transport, and then all of the calcium will go into the sarcoplasmic reticulum, and then what will this calcium do? It will also go into the sarcoplasmic reticulum, and then since there's no more calcium on the troponin C, this will again go back to its original place and prevent the interaction of myosin to the actin, and then the muscle will slide and go back to its original position. So that basically sums it up. A relatively easy topic. Try to, especially this spot, this sliding filament mechanism, try to read it first and then watch some animations, and then you'll get the hang out of it.